Part 2 of this video. Maybe we'll get some test numbers. So I forgot to mention in the first video, it's important that these magnets alternate north, south, north, south, north, south. Doesn't really matter which is north and which is south, but when you're putting them down, you need to be sure they're opposite. A good way to do that, remember with magnets, like poles attract, opposites repel. So if I'm holding this magnet over this one and it repels, I keep it the same way and I put it down there. If it attracts, I need to flip it over, because if it's repelling on the back side, that means if I have a north here, I have a north on the bottom and I have a south on the top. So I can lay it in there like that. When you got 4 magnets this close together, it's pretty obvious too. If you try to put them in wrong, this one won't want to slide in there. It'll repel away. If it attracts into the square, then it's good. The glue here is dry. All the glue is dry. So let me see if I can undo that real quick. So that's cool. That coil should go right into the test over here. I'll put it in the vise and get it where I want it. It's off topic, but I also use vices to test flux between air gaps. So sometimes I'll put magnets on each side and use a Gauss meter in between here to figure out how much flux I've got, or the field density in between. And that's useful in figuring out how thick to make coils. The thicker you make the coil, of course, the more windings you can get, the more voltage you can get, but the less the flux there is. Stronger flux with no air gap at all, but there's no room for copper. So somewhere is the sweet spot. Usually the sweet spot is to make the coil about as thick as the magnets, which is what I've done here. So now I've got this set up just the way I want it. See, the magnets are running very close to the coils, or to the coil. I've already stripped the wires, so I'll hook those up in a minute to the meters. I've got a rough speed indicator here, but I can also use frequency to look at speed. I think I will get 1 hertz per 30 RPM. We'll see if that agrees, if my math is right, with a 4-pole alternator. So right now I'm at about 260. I suppose I should expect somewhere around 5 hertz if I look at frequency. And we'll see what kind of voltage we get here in a moment. It paid off to take time to make everything square. You can see that this actually runs really well. Okay, so it's all set up now. This meter's looking at hertz. That's an indicator of RPM. 30 hertz equals, or 1 hertz per 30 RPM. 10 hertz will be 300 RPM. I've already dialed it in at that, so our test will start at 300 RPM. Voltage is exactly related to RPM, so if I get whatever voltage I get at 300 RPM, I will get exactly twice that at 600 RPM. So I'll start the machine. So my indicator up here is a bit off. It says 280, but 10 hertz means 300 RPM exactly. And there's about 0.66 volts AC. I could play with coil positioning and see how perfect I got it. As far as in and out and side to side goes, you can see it's pretty forgiving. So here I'm moving the y-axis. So I can have 0.67 volts there. And I can play with the x-axis. That's not mattering much. We're pretty perfect on that. So I could speed it up just for fun. This is about where I'm sure magnets would fly out if I didn't have that cage on it. That says 400 RPM. It's probably about 450. Well, 13 hertz. Oh, wrong knob. You can see what happens with the distance here. Look at the meter, and when I go up, see how dramatically it drops off. Half a volt. I'm just nicking that wire over there. So we're at 1 volt at 14 hertz. But anyhow, the easy data, 0.7 volts at, well, 1 volt at 14 hertz. We can do the math on that. So I never intended really that 21 gauge and 180 turns would be what we want. But from that, again, I can extrapolate. If I use wire that is half the cross-sectional area, which would be number 24 gauge, I could have twice as many turns, and then I'd be getting 1.4 volts at 300 RPM. If I put this in single phase configuration with 2 coils in series, I would double that voltage. So I would have 1.4 volts AC, RMS AC at 300 RPM. If I added a blank steel disc on the back side of this to help complete the magnetic circuit, because the flux flows from pole to pole, the flux would then, instead of going out of one magnet kind of into space and then maybe some of it finding its way around to the next magnet, it would be going directly into the steel plate behind it, through the steel plate and back to the magnet next to it, and it would increase the flux by about 50%. So if I did that, one blank steel rotor back here, I would expect about 50% more voltage. If I put another steel disc back here with magnets on it, same as this one, in attraction, so that wherever I have a north pole here, I have a south pole down here, and vice versa, that would double the voltage. So in this case, if it was a single phase machine, I could double the voltage, and with 2 coils, and double it again with a second rotor with magnets. So then I would be getting 300 RPM. I would be getting, let's see, 1.4, about 3 volts at 300 RPM. That starts adding up quickly, because then if I went to 24 gauge, I would have 6 volts. It'd be 24 gauge, 360 turns of wire. It's a bit tough with these magnets on these 4-inch discs. If we could expand to 5-inch discs, then I could fit 4 coils instead of 2 for single phase. and then quadruple it with the same number of magnets. And if we only used 2 coils or did 3-phase, we could fit a lot more turns per coil. So anyhow, there's some thoughts and a quick test of what to expect from these magnets and that particular coil. And that's actually quite a lot of data to work with these magnets.